Welcome to Chapter 2, Section 6, and this is the second derivative. And what we're going to talk about with this second derivative is called concavity. Notice that a function can be concave up regardless of whether it is increasing or decreasing. So that's pretty important. Notice here, if I were to talk about the slope, here we would have a negative slope. Here it goes to 0, and here it's a positive slope. But all of that is concave up. Same thing here. This is all concave up. Because if I just look at that part of the graph, it's opening up. So in this figure here, F is concave down at now. Okay, so they're calling this point here now. The slopes are decreasing. So why would the slopes be decreasing? If you think about what the tangent might look like here, that has a much greater slope than that blue line. And then after the blue line, we're getting closer to 0, aren't we, for the slope of the line? So what they mean by decreasing is that it's literally the slope is getting smaller. It doesn't have to do with positive and negative. This graph right here, we can see is concave down because everywhere here it's concave down. So in B, it's concave up. The slopes are increasing. So we started here, let's say we start here at 0 or almost 0. As we go up this curve, the slopes of the line are getting steeper. So the difference between the graphs come from whether the derivative is increasing or decreasing. So remember, if I have graph, I start with a parabola because we're all really familiar with a parabola. Okay, here's my parabola. Now, if I say I want the tangent at point 1, 1, so 1, 1 is right here, and the tangent line is pretty steep there, right? But it's positive. I mean, we can figure out what it is, but it's pretty steep and it's positive. If I take the tangent line right here at -1, it would look something like this. Okay? And that's so the differences between the graphs come from whether the derivative is increasing or decreasing. The derivative of a function f is a function that gives information about the slope of f. The derivative tells us if the original function is increasing or decreasing. Okay? When we have a negative slope, this would be a negative slope, it's decreasing. When we have a positive slope, it's increasing. Now we have something else we want to know about, the second derivative. The second derivative gives us a mathematical way to tell how the graph of a function is curved. So the second derivative tells us if the original function is concave up or concave down. So what does that mean? Well, let's take a graph. Let's do x to the third. Okay. Well, if I start at 0 and I go to the right, This definitely looks like it's opening up, right? Everything's pointing to this opening up. But somewhere something happens because here it looks like it's pointing down, right? So this would be considered concave up. And this would be concave down. So let's talk more about it. The second derivative just really means once we take the derivative, we call that the first derivative. If we take the derivative of that derivative, that's the second derivative. Okay? So using prime notation, this we can say is f double prime, y double prime. Find f double prime for f of x equals 3x squared. Okay, so f of x is equal to, 3x to the 7th. The first derivative, which I say 1 prime, is equal to 3 times 7x to the 7 minus 1 or 6th power. And this is equal to 21x to the 6th. That's my first derivative. My second derivative, I take the derivative of this. That's going to equal 21 times 6x to the 6 minus 1, which is 5. This is equal to 126x to the 5th. And I could keep doing this until I run out. At some point, it's going to be 0 because I'm going to go to a constant, then I'm going to 0. Okay? That if I have a graph, okay, so let's make this -1 and +1. And when the function is 0, when x is 0, y is 0. Between this 0 point and this 1 point, the graph is going to be very flat, and then it's just going to soar. Same on the negative side. It's going to be very flat, and then it's going to soar. But it's going to look like x to the 3rd because they're both odd functions. Now, let's go one step further because we have been kind of talking about the second derivative. So the second derivative here, well, I know when x equals 0, f double prime equals 0. And I know that when x equals 1, f double prime is equal to 126. And when x equals -1, f double prime is equal to -126. Okay, so that means 0, this place right here, is a transition point between y being positive and negative. And from that point to the right, we can see it's concave up. All this is up. And we can see, hopefully, that all this is concave down. It's opening down. That's why I'm drawing, the way I'm drawing it is the way it's opening. So just like we said, notice when it's positive, it's positive. When it's negative, it's negative. If you were to draw a parabola next to it, a positive parabola would look like this. A negative parabola would look like this. This is concave down, and this is concave up. So since we're talking about the derivative in terms of velocity and speed and distance and acceleration, what I'm going to do is I'm going to say, when do I know I'm going faster? Well, for me to go faster, that would mean that the derivative, which is the same as velocity, is great. So I'm going forward. Right? When it's greater than 0, I'm going to say that I'm going forward. Then if I put my foot on the accelerator, that means F double prime is also greater than 0. And I'm going faster in the forward direction, so this makes faster. If I'm going forward and I accelerate positively, I'm going faster. Now, look at the contrast. If I have my f prime of x, which is the same as velocity, and it's less than 0, so I would have f prime of x less than 0, I'm going backward, right? Because we're using velocity, and velocity actually has a direction. So here I'm going forward, and here I'm going backward. That my velocity is going negative. Now, if I'm going backwards and I accelerate in the positive direction, so I'm going backwards, I put my foot on the accelerator, and at the exact same time, I put my car in drive instead of in reverse. Let's just say my car doesn't fall apart. What's going to happen is I'm going to start slowing down because I'm accelerating in the opposite direction that my velocity is. I really hope that made sense. Now, what if my velocity is negative? So let's say my velocity is negative. So it's less than 0. Now I'm going backward. Okay. If I accelerate in the negative direction, I'm still going faster. I'm just going faster backwards. Okay. So opposite now. If I have f prime of x is greater than 0, which means I'm going forward again, and I put my foot on the brake, so here I'm going to brake, that means I'm accelerating in the negative direction. Because I was going forward, now I put my brake on, it's the same as having the accelerator go in the negative direction, and I start slowing down. Hopefully that made sense. That's a very important concept, and it's a little bit hard to understand sometimes. So example 2, the height of a particle at time t seconds. So the height in feet of a particle at time t seconds is this function right here. This f of t is equal to the height, and the units we're going to use are feet. Find the height, velocity, and acceleration of the particle when t equals 0, 1, and 2 seconds. Okay, so f of t is equal to t to the third power minus 4 x squared plus 8t. Now, it asked me 3 questions. It asked me to find the height, velocity, and acceleration of the particle at these 3 points. Well, we could right now go and find what the height is at t equals 0, 1, and 2 seconds. This is the height at f of 0 equals 0 because I'm replacing my t with zeros. This is 0 minus 0 plus 0. Everything has a t, so there's zeros. So now I know f of 0 is 0. Now, when when t is 1, things are going to be a little different. So at 1, it's going to be equal to t to the third, or 1 to the third, minus 4 times 1 squared, plus 8 times 1, which is equal to 1 minus 1 squared is 1, so 1 minus 4 plus 8, which equals minus 3 plus 8, which equals 5. Okay, the function is at 1 second, and f of 2 is equal to 2 to the third power. And this is not an x, it's t. I have 2 to the third power minus 4 times 2 squared plus 8 times 2, which is 8 minus 4 times 4 is 16, plus 8 times 2 is 16. This gives me 8. So we know the height here is 0 feet, because remember, it told us this is feet, and this is feet. But I only found the height. That's all this is the height. Let's talk about velocity. So my first derivative, f prime of t is going to equal 3t squared minus 8t plus 8. And if I want to know what's happening at each of those points, I would say f prime of 0, and I'll plug 0 in for all my t's. This goes to 0, this goes to 0, I get 8. I plug in f prime of 1, I get 3t squared, so it's 3 times 1 squared minus 8 times 1 plus 8. You don't have to do all these ones. I'm doing it just to make sure everybody understands where things are coming from. So this is 3 minus 8 plus 8, which will give me 3. And then I have f prime of 2. That's equal to 3 times 2 squared minus 8 times 2 plus 8, which is equal to this is 12 minus 16 plus 8. 12 minus 16 is minus 4 plus 8 is 4. So now I know what my velocity is at time t equals 0, t equals 1, t equals 2. So my acceleration, which is f double prime of t, or the second derivative, or the derivative of the derivative, is 3 times 2t, or 6t, minus 8, and my constant goes to a 0, so this is my second derivative. My values here are f double prime of 0, that equals negative 8. f double prime of 1 is equal to 6 times 1 minus 8, which equals minus 2. And f double prime of 2 is equal to 6 times 2 minus 8, which is 12 minus 8, or positive 4. So why is this happening? What is actually happening? Well, let's analyze it. At t equals 0 seconds, we said our height is 0. So we didn't go anywhere. But we said our velocity is 8. So this is basically, we're starting at the beginning, we have gone nowhere, but we have a velocity of 8 feet, because that's in feet, and t was in seconds. Okay, so at t equals 0 seconds, what's happening? My position is 0, so I haven't gone anywhere. My height. Okay. My velocity is positive, because it's 8 feet. It's 8 feet. It's actually 8 feet per second. And my acceleration which is f double prime of t, is negative. That says a lot. That means I'm starting somewhere. I put my foot on the gas. I'm going forward, but someone's putting their foot on the brake, because that's the only reason that my acceleration would be slowing me down. So here, this is not me speeding up. This is me slowing down. So at 0 seconds, I'm slowing down my height with my height. Okay. Now, at f of 1. So at f of 1, my height is 5 feet. Or t equals 1 second. My height is equal to 5 feet. F prime, my velocity at 1 second, is equal to 3. 3 feet per second equals 3 feet per second. Okay, going forward, my acceleration, f double prime of t, is equal to, at f negative, still it's slowing down, -2 feet per second squared. So even at 1 second, I'm slowing down. Talk about 2 seconds and then we're done. So t equals 2 seconds. My height is 8 feet. So my height equals 8 feet. My first derivative, my velocity, when t equals 2, is +4. This is f prime of t equals 4 feet per second. And f double prime, okay, f double prime, it's my acceleration, is 4. It's my, everything's 4. Okay, so now this equals 4 feet per second squared. Okay, so I'm somewhere, I'm 8 feet high. I'm going in the positive direction, 4 feet per second, and I'm accelerating in that same direction. So here I'm speeding up. Because my forward motion of my velocity and my acceleration being the same, it speeds me up. Okay, so now we're going to talk about inflection points. Remember we talked about the second derivative, and we talked about concavity and opening up and opening down and positive and negative. Well, between positive and negative numbers, remember there's a 0. So for an inflection point, an inflection point means we're changing from concave up to concave down, or vice versa, concave down to concave up. So when that happens, what has to happen is the second derivative has to equal 0. Here we can see at A, it's concave up. And at C, it's concave down. So I'm going to say at B, this is an inflection point. Right somewhere around there, it's changing its concavity from concave up to concave down. Okay. D, again, looks like, no, it actually looks like all of this is concave down. So I'm going to say from B, and actually all of this till G looks like it's concave down. How does that happen? This C is a cusp, but everything is opening down until I get to G. I'm thinking G is my inflection point. Why do I say that? Because H is opening up again. Okay, so that's what concavity looks like. So inflection point's happening when the concavity changes, because we know that the connection between the concavity of a function and the sign of its second derivative, we can use this to find inflection points. So the working definition. An inflection point is a point on the graph where the second derivative changes sign. Where would it change sign? Where I said when it's equal to 0. Note that it is not enough for the second derivative to be 0 or undefined. We still need to check that the sign of f double prime changes sign. And I'll show you exactly what that means. The function in the next example illustrate what can happen. Okay. So example 4. We have f of x equals x to the third power, g of x equals x to the fourth power, and h of x equals x to the 1/3 power. For each of these functions is the point 0, 0 an inflection point. So the question actually reads, let's say we have a number line. Well, f prime of x is going to equal to 3x squared, and f double prime of x is equal to 6x. So if I want to know, do I have an inflection point? Well, This is my second derivative. So if I want to know whether or not I have an inflection point, I have to say, let's see if it equals, where does it equal 0? So when x equals 0, y equals 0, and I have my first inflection point, or my first possible inflection point, because I have to check to see what signs are on each side. So let's plug in 1. F prime of x equals 6 times 1. Okay, that is a positive. So on this side of 0, because it's going to stay positive, doesn't really matter what I plug in for x, we have a positive concavity, which means it's opening up. And on this side, we have a negative concavity, because these are all negative numbers, -1 to the 3rd power. I'm sorry, -1 times 6 is -6. That means everything to the left of 0 is negative. And so 0 is 0, 0 is my inflection point. Because notice I am changing direction. I am changing signs. So x cubed, 0, 0, we have an inflection point. All right, so now we have g prime of x. That's going to be 4x to the 3rd power. G double prime of x is going to equal 4 times 3 is 12x squared. Okay, let's do our number line. At 0, this function is still 0. Okay, I have my inflection point, or my possible inflection point, I should say. Well, when x is positive, I know that. And what I really want to know about is my second derivative, because it tells me about concavity. So when x is positive, this is positive. And when x is negative, oh, I'm squaring it, so it's going to stay positive. This has no inflection point because it does not change concavity. It's going positive and then positive. No inflection point. Okay, and last we have h prime of x, which is equal to 1/3, and then 1/3, the exponent is 1/3 minus 1, which is -2/3. So we can say x to the -2/3, but that's the same as 1/3 times the cube root of x squared. Okay, that's my first derivative. My second derivative well, I have this 1/3 times, I'm going to use this part of the function to take my derivative because it's easier. I just subtract 1. So I have x to the -5/3. -2/3 minus 1 is -2/3 minus 3/3 equals -5/3. Which is really the same as 1/5 times the cube root of x to the 5th power which is equal to 1 over 5x times the cube root of x squared. So hopefully you know your exponent rules well enough. If you don't, just come to my office hours or, send me an email and I'll get together with you and I'll explain it. So there's many different forms that this has taken. I said it could equal this. I said it could equal this. And I also said it could equal this. They're really all the same. So let's look at our number line. When x equals 1, well, my second derivative is what I'm graphing right now. So I have a positive for x here, and I have everything's positive. So I can say when x is greater than 0, I have a positive. Now, when it's negative, I have this is negative, that x is negative. Well, I'm squaring the negative, which makes it positive, so I'm going to have a negative value on this side. And now I know I have an inflection point. At 0, 0, I have an inflection point because notice it's changing concavity. It's going from negative to positive because I'm looking at my second derivative. Sketch the graph of a function with f of 2. So at x equals 2, y equals 3. F prime of 2. So we have a positive slope there. That means, and it's 1. So I don't know what this function looks like because they're not telling me, except that they're telling me it has an inflection point at that point. So that point is an inflection point. Okay, so that means I can go from concave down to concave up, right? I could have a graph that looks like that, or maybe it doesn't curl around, but looks like this. Okay, so this would be an inflection point because I'm opening down on this side and up on this side. And my f prime at 2 is positive. Okay, this would have a positive slope. I'm not actually figuring out what the slope is. Maybe it would change a little, but I have one possibility for what it could look like. So what else could it look like? Well, two, we have a point, and now we're going to do the opposite. How about if I do concave up and then concave down? Then this point would be, again, an inflection point, and my tangent line would look something like that. And it has a negative slope. Well, that can't be it because I'm not supposed to have a negative slope. I'm supposed to have a slope of positive 1. So that didn't work. What else could we do? Well, I know now I have to have at 2, 3, I have to have a function with the slope of positive 1. And I already have concave down to concave up. I want to have concave up to concave down, and that I want that to be my derivative. So let's see, this might work. Concave up to concave down. Okay. Do these look the same? No, they look different. See? This looks like this. And this one looks like this. So this is concave down and then up. This is concave up and then down. So those are the two that I can think of. I think there's some graphs down here. Let's see. Okay. Thanks for watching. I'll see you soon.